Great, thanks so much. So welcome back, everyone. And I guess I should first say, thanks for joining us also in the Our Town virtual world. I know that there's been a little bit of a learning curve, I think, for all of us, and we appreciate your bearing with us as we try to navigate these sort of strange times. So I'm really excited about this afternoon's panelists, I guess. I think we're going to have a great discussion. There's some super interesting talks. I hope that everybody had a chance to watch them. So first up, we're going to talk to Besmira Nushi, who joins us from Microsoft AI Research. And the work that we'll be discussing concerns the super important, timely, and practical issues around kind of safely and robustly deploying machine learning models. And I think what I'll do is I'll start by asking Besmira to give us a brief summary for the benefit of folks that maybe didn't have opportunity to watch the talk, although they should. It's great. And so maybe if you could just give us the high-level overview of what your work is about and what your talk was about, that would be a great way to start us off.
Mm-hmm. Thanks, Baron, for having me and the organizers. Yeah, so I tried to summarize in the talk some of the ongoing work that we are doing at Microsoft and Microsoft Research on deploying reliable and human-centered machine learning systems. And I tried to explain what does that entail, and the fact that while we all care about reliability and robustness in machine learning, when it comes to doing it in the real world, if you are a machine learning engineer or practitioner or somebody that is just trying to understand whether an AI is good or not for deployment, then these tasks are very hard. They are sometimes manual, tedious. You have to do a lot of background coding and scripting to really get to the answers that you want. So basically, you do need some automation with respect to tools for developers. And given that we are now close to several decades of software engineering as computer scientists, and we have built tools for software engineering, due to the recency of having machine learning deployed in the real world, we still are not there yet. With paving this path of building tools and having things available for developers. So this is basically what we're working on now. We have built a tool that we call error terrain analysis for understanding how cases where the machine learning model fails and those where it succeeds are different from each other, mostly to characterize how the error boundaries develop in a machine learning model, so that we go beyond those types of performance reports that we so much like in leaderboards, where we say my model is 90% accurate, the other model is 85% accurate, and forgetting that in general model performance is not uniform. There are cases or subgroups where the error rates are much higher, and we need to know about and be able to find them. And the same question, when these models are updated or retrained with more data, we still need to be able to understand whether there have been cases where the new model is perhaps wrong and the old model was right. And how does that break trust in usability? And
yeah, so I thought that was a really interesting perspective. You sort of view this as, I guess, maintaining. I think this is the notion of backwards compatibility. Is that right?
Yeah.
As you characterize it.
Yeah.
So I was wondering, as you were talking about that seems quite intuitive to me, at least. This notion of you don't want the model to, after you update it, all of a sudden sort of make different mistakes than the kinds of mistakes it made before, even if the overall or sort of aggregate measure of performance is comparable or even better. But I wondered, have you done human studies on whether that's intuitively agreeable? But have you sort of investigated whether people in practice are particularly concerned about this?
So we did some user studies in a game-like domain. There is a platform out there that is deployable in Mechanical Turk and in other crowdsourcing platforms, where you try to see whether people are building mental models of these error boundaries, where the AI makes a mistake and when it doesn't. you try to see how that mental model develops over time and whether it breaks at the moment when you deploy an incompatible model. And we do see that that type of disruption does happen. People can recover, but the recovery time depends on like how incompatible you are during deployment.
Sure, that makes a lot of sense. So just as a reminder to folks, if you do have questions, please enter them in the GoToWebinar question system, and we will try to field them as we go. I guess while we're waiting on the audience to do this, another kind of question that I had as a sort of a high level question, I guess, is as somebody that thinks a lot about deploying these models and not just kind of, I don't know, eking out some score on a leaderboard or something. What are, like, in your opinion, what are the sort of main blind spots that folks doing the research, sort of more on the research side, often overlook? Like, do you have a sense of things that maybe researchers should focus more on in their work?
Yes, so there are quite a few things that in research, and I take my blame for this as well, because we sit at Microsoft Research, but we do get this visibility from the product teams. So something that sometimes we tend to overlook is the need for infrastructure. And things that need to come together with the infrastructure. For example, how do you construct a good testing suite? Like what are the good properties of building a benchmark for your system?
I see.
And these types of things, we know how to do them for classical software engineering because of years of experience. But in machine learning, every different application has its own implications, societal implications, fairness, and error distribution implications. And those things are currently difficult, and they are also an open research problem.
Yeah, that makes a lot of sense. So we have a few questions. So one question that's come up concerns this result you mentioned, that greater explainability could in fact lead physician collaborators astray. And they were interested in basically just hearing more about what you observed here. That seems to spark their interest.
Right. So what we observed in these were studies done in 3 different language domains with highlights of explainability per word, like the classical one. And sort of our assumption there was that by changing the way how we show these explanations, like showing, for example, one class explanations when the model is confident, and 2 classes, it was a binary prediction in that case, when the model is not confident, then maybe we would give this signal to the user that this is a low confidence prediction, maybe you shouldn't trust the model that much. And I think it made it it improved the way how people were following the model, in that they were not always blindly, following the predictions, but trying to be more cautious. So basically what we wanted to see is lower agreement rates for when the model is wrong. However, there are things that are not yet solved, even with this type of strategy. And the first thing is that even when the model has high confidence, sometimes it fails. And this is the problem of, for example, out of OOD, out of distribution data, or unknown unknowns, things where we fail with high confidence. And in that case, the explanations that we currently have cannot convey that part. So that is for one. The other thing is, when the model has low confidence, as a human, okay, you understand that the model probably might not be right, but maybe in that case, you also do not know how to solve that task. So how can you work together? Like, how can these explanations help me to get better insights on the problem and try to solve the task better? And I think that piece is again missing in what we have.
Interesting, thank you. Yeah. So coming back to, I guess, the notion of disparate kind of performance across subgroups, you, I think, suggest a system that you call Pandora. Could you say a bit about what this is intended to facilitate?
Right. So Pandora was the research methodology that we proposed in back in 2018, and since then we have built an actual tool internally at Microsoft that we are hoping to make available, open source, perhaps by the end of the year, beginning next year, in the form of Jupyter Notebook widgets. Also, the tool will be first available like that, and this is a set of modular visualizations that can help the developer to separate the cases where the model fails and where it doesn't. Basically, to understand what are those features that are highly correlated with failure. To be able to do this in-depth performance reporting.
And are the features then features in the traditional sense that are literally going in as predictors, or are these sort of metadata? So I guess what I have in mind are things like demographic information or something like that. And of course, they may be both. But I guess my real question, and I think this is echoing one of the questions we've got from the audience as well, is like, do you assume that these are kind of supervised in the sense of like, you know, that these are the maybe classes of instances that I want to look for differential performance on, or are you able to uncover these clusters in an unsupervised way?
So this is a great question, and I'm happy someone asked and you asked. I think in order to really, you know, do in-depth performance reports, we need all of this features and all of these approaches. The ones that we have used so far are the actual features that the model is using. We're using extra metadata like demographics that you were mentioning, if it is available in the benchmark. Other metadata that maybe you collect with crowdsourcing. Another interesting type of metadata that the larger teams have been using while using our tool are system execution signals that are coming from the larger software system. For example, maybe you have a recognition model, like an object recognition model that is running on your camera. And the model knows what it knows about the image and so on. But then we also try to include things like the angle of the camera or the depth of the camera in that moment, or properties about the device and image quality. So things that are surrounding the model that are maybe outside of the model, but that may be environmentally impacting its quality.
Makes sense.
Yeah, and then another thing that we are doing now is we're working on automated feature extraction, semi-automated. I don't want to call it automated because this is like feature representation is a hard problem in machine learning, and we're all trying to improve it. Yeah, we're trying to semi-automate the feature extraction part and label those features and reiterate.
Great, yeah. So there's a question coming in now also about checking the reproducibility and transferability of data for external validation when we have, I guess, different populations but the same features and outcomes. So I guess this maybe what this question is getting at is perhaps a limitation that's, I mean, inherent, I guess, to working with supervised data. You sort of have the data that you have, right? And all of these checks and whatever that you can run, unfortunately, you're sort of constrained to the data that you're applying it to. And of course, you know, we typically make the classic IID assumption at test time, but in practice, of course, this is not the case. And I guess how do you have you thought about that, and sort of how do you view the world of kind of once you've deployed the model and it's seeing some other distribution? How might you anticipate, I guess, disparities in outcomes that might subsequently arise in practice? I wonder if you have any thoughts on that.
Right. So here's the thing. Like currently, we need to have these types of performance evaluation reports transparent, interactive, and available publicly. In that, if I'm a customer and I'm trying to buy, you know, or to use an API for object recognition or something else, and maybe I have my own data that I want to test this model upon, I should be able to have it even before I buy, to run the API and see how it performs in my own benchmark. and have detailed and interactive performance reports. And I want to emphasize the interactive part, because performance reports are not a static thing where like I show you a number or 10 numbers, and those numbers do not change over time, or those numbers do not change if I change the group of focus from the data. So that needs to be available. And then I know that perhaps this is deviating from the overall performance with X number, but as a customer, I know about this and I make an informed decision.
It's really interesting. It almost suggests that perhaps in the future, the emerging sort of position will be like somebody who does effectively QA, but for these models explicitly. And so you can imagine like an entire field of people that are like trained to basically to poke at these models with respect to various concerns. Maybe this is already happening, but that's actually like a really interesting direction to think about.
It is happening, and I want to call, like, one of the first studies that tried to put some structure into this process was a gender shade study for the performance of face processing algorithms. But the thing is, like, every time you have to do this, you have to write your own scripts and reinvent the wheel every single time. And the question is, like, how can we facilitate this type of work?
How can you make it more consistent? Exactly.
Yeah.
So we're coming up onto our time. So I guess what I would like to do is give you opportunity to give us any kind of key takeaways you'd like to leave the sort of audience with, and things, particular thoughts that this audience might benefit from the perspective of developing more robust deployed systems and how we might get there.
Well, I'll try to repeat a few thoughts that I said towards the end of the presentation. I think the value of collaborating with interdisciplinary communities is that we can actually come up with solutions that are informed by what practitioners need out there in the field. In that, if we design for human AI collaboration, for instance, like these types of explanations or other forms of interactive collaboration between human and AI, I'm hoping that as we go and collaborate more, we'll be able to inform these studies even more with large-scale studies with medical professionals that are taking decisions out there in the real world, so that we build the right tool and so that we design the right machine learning model.
Great, yeah. So it sounds like you're hopeful about our ability to do this, and so hopefully you'll keep up the good.
I actually saw some very good papers that I'm looking forward to read in the conference with these types of studies. Yeah.
Good. That's great to hear. So I think with that, we'll sort of close out this first session. So it's always awkward. There's no like applause as we would normally have for speakers. So I'll do it on behalf of everybody for your contributions. And I hope everyone, again, if you haven't watched the talk, go watch the talk. And I guess we will plan on returning after a brief break here. But of course, you can kind of stick around, and we'll be back in 10 minutes or so with another interesting speaker.
Thanks, Baron, for hosting.
Thank you.